So, for instance, the constants to use the same they had there could be lambda 1 u cross Laplacian u minus lambda 2, or it's better maybe to write plus lambda 2 bracket minus u cross Laplacian u. And microphone. One second. Okay, can you hear me? Does it work? Your question? Okay, so so these are the Landau-Lifshitz equations I wrote yesterday. Let me say that we need lambda 2 to be, say, largely equal to 0, and lambda 1 can be any real number. I will come to application in a moment. What I only want to say is that if we look at this equation from the point of view that Laplacian u is the gradient with respect to L2 norm of the energy function of u, where E of u is 1/2 gradient u squared dx, for all u, say, h12 function with values in R3. So the gradient in the linear space, then this equation can be written also as lambda 1 u cross gradient E minus, let me put here, still plus lambda 2 minus u cross gradient E. Actually, to be precise, I used yesterday this notation to denote this. And with this notation, it is clear that we can replace this energy, which is called exchange energy, by energy which contains also other terms. And the other terms could be, for instance, integral over d of some function of phi of u of x dx. So, and then we got slightly more general equation. Now, about the application. So, these equations come in the study of ferromagnetism. Below the Curie temperature. That is, I just kind of copied the last one, because what apparently it is that below the Curie temperature, the length of the vector u can be kept constant. So what we want, we have initial data, u0 of x, and we assume that the norm u0 of x is just equal 1 for every x. So the u is the magnetization vector of the domain of the magnetic material. There is a special case of these equations, which have been actually very extensively studied by physicists in last at least 20 years. This special case is when the Laplacian term is 0. So I didn't put here, could have put here some constant, put it. And for us, epsilon was 1, but if we put in this exchange energy 0, then the energy becomes just this integral. And in this case, one can look at constant solutions, constant respect to x. And what we get? We get the equation which will look like du over dt, so there will be no x variable, equals Laplacian u. This guy is, sorry, now I remember. There was always minus. Yes, it is minus gradient. So it will be cross minus phi prime of u, of gradient phi, minus plus lambda 2 minus u cross gradient phi. And these are the equations which can also be written as a gradient with respect to energy with values in R. So if I denote now phi of u is the integral of phi, if I denote by phi of u, not the integral, because now we don't have integral, but phi of u, for u, a function element in the sphere, then this equation can be written in the as a gradient equation, this part, on the sphere, and there's some rotation part over it. So these equations are a special case, and they describe the behavior of a magnetization of a very small magnetic material where the dependence of variation on x can be not taken into account. So there is a sort of material with a constant magnetic field around the whole material. And there are many such people who studied this. I only mentioned the word Chantrel because it's a physicist from University of York. I don't remember his name, but there was a whole industry on such problems. But actually, they are not studying those problems because they are ordinary differential equations. As I mentioned, the people were studying equations with noise, with stochastic differential equations, and they were studying because of these observations and suggestions made many years ago by Neil and Brown, that in order to understand transitions between many of different stationary solutions to these equations, you need to consider temperature or noise. And what these people were doing, they're considering stochastic version of those equations. And at the end, it is a paper by Van den Eyden, Kohn, and Reznikov in 2005, I think, who studied this equation with noise from the point of view of large deviation principle, finding potential function, and so they consider this case when the epsilon goes to 0 and finding certain estimate. It was always Gaussian noise, yes. I have spoken only Gaussian noise in this lecture. And anybody interested in this field could look at it. Also, from the pure mathematical point of view, as Professor Freidlin has observed, there is nothing new in this paper, but just applications of his theory. So in a sense, he is right, but nobody has written this application before them. So in that sense, it's interesting application. Yeah, that's the point, yes. That was what they observed because, but actually such an observation is already in Wenzel Freilin book. Yeah, but they had a lot of analysis, etc., etc. So it's, the point is that it is important paper, although mathematically it does not develop new techniques. So in that sense. Now, they all already observed that it is interesting to study the case of materials which are not uniform, so where this U depends on the position of the particle in the material. And it turned out that the deterministic version of Landau-Lifshitz equation has been already studied, and the paper which we have taken to understand, it was a paper by Visintin in 1985, I think, or 6, I think. Anyhow, and who really studied not only such equation like this one, where we have general energy coming here, this gradient could be really replaced by, so this is like a constant Laplacian in the end. When you get with a constant coefficient second order operator, you can have operator which has non-constant coefficient. And you have also much more general situations which involve magnetic fields, etc. In the stochastic case, this general situation is being investigated by Liang Li, who is here. And today I will really concentrate on the simplest case where epsilon is 1 and we have no phi. If there's no phi, it is enough technicalities to look at this problem. And in the second part of my talk, I will use some slides which I prepared earlier and show you some possible applications of what we are doing here. So, coming back to the problem, what we have this equation, and in these equations we can just put maybe lambda 2 to be 1. We can always do it. And also I want to remind you that yesterday I wrote a form that this equation is equal to u Laplacian u plus gradient u squared u, which is true for, say, smooth solutions. But today we'll really use the form, this one, with the vector product. So this is just for a reminder. And since we have some space, let me write it down. Here we consider Neumann boundary condition and initial data U0, which we assume to be in Sobolev space H12D with values in S2. So whenever I write M, I will mean S2, because, and so this condition actually means that your initial data has originally values norm of length 1. And as a noise, the sort of way the physicists introduce the noise, they said that the noise should come into this part where we have Laplacian. So it should be like perturbation of the gradient of phi. So if it is like that, we should have a noisy term here and noisy term there. So again, the u was missing. So if you do like that, formally speaking, the noise should be the form u cross some noise from one part, and from the other part should be u cross noise. And you recognize from my first lecture that this sort of equation is equation when we consider Brownian motion on the sphere. So this, if it was only this guy, would have the Wiener process in R3, and this would be the projection on the sphere. So this is the guy which again corresponds like this gradient flow. The other one is the flow which moves in the perpendicular directions. So if you look at this situation on the sphere, one noise wants you to go in this direction, another in the perpendicular. And physicists were interested in stationary solutions, in fact. And in those simple versions, you can actually prove the exist stationary solution simply because the state space, which is sphere, is a compact manifold. And when you have a stochastic differential equation on a compact state space, and if it generates a Markov semigroup, there is always invariant measure. And Professor Sundar, who spoke about this, could confirm, but he is not here. And he mentioned Krylov-Bogolyubov technique, and he used it somewhere to say that something is compact. Yes, to estimate here, there's no need to prove a compactness because we have a compact state. This is not the case of the full equation, and whenever we add the noise, sorry? Yeah, so but in fact, if you have a probability measured on compact set, they're always tight. So the state space is this one, or is state manifold. It's not compact itself. And we so far don't know how to prove existence of invariant measure. So this is kind of an open problem. And coming back to these models, so many physicists, because they're interested in invariant measures, they observe that actually if you have these equations, or just this one, you have invariant measure, and they are differ by some scaling. And it actually simplifies when we only consider noise in this term. And Liang, again, is working on the other case, which is more complicated because you have two U's, one here, you have only one U. Yeah. And also you remember that when we want the thing to be constrained, we need to consider Stratonovich integral. So this should be not anything, but it should be Stratonovich integral. And at the end, what we put as a noise, we consider as a noise of the form. So this would be some vector h of x multiplied by one-dimensional Wiener process. So this equation which we have to add here should be not should be plus u cross Stratonovich form h w. So this has also has to be Stratonovich. It is not that we want it nicely, because actually, in order to prove this theorem, we use the fact that it's Stratonovich. Thank you. And just to maybe finish the Stratonovich picture is that, so I can even write it down something like that, I don't know. It's a question of notation, yeah? Because what we want to consider a map G of U, which is U cross H. Remember, we took H, certain vector field on D, I think W14 or something like that. We fix it, and we consider a linear map G of U, and then in the Stratonovich form, we need to consider G prime, but G prime on U is a linear map. So G prime on U in any vector is just V cross H. And then we have to consider G prime on U acting on G of U. So if you apply this formula, what we get, you get U cross H for V and cross H again. So if you want to write down our equation in the Ito form, and this proves because I really use the Ito calculus, I mean, I use the Stratonovich idea to write down the equation. So this part should be treated U cross H dW plus 1/2 U cross H dt. That is our equation in Ito form. And they said it's somehow easier to make no mistakes when we use the Ito form of the equation. And analysis which we have is for the Ito equation. So when we want to solve that equation, we need to ask how we define a solution. So first of all, as you have seen yesterday, there is a problem with this Laplacian. So actually, we don't know, in generality, whether this equation has a solution in the strong sense. So whether we can say what does it mean Laplacian U and U cross Laplacian. Because if U is only in this space, Laplacian U is a distribution, and then we have to multiply a function by a distribution, and then becomes a problem. So what we want is to give a meaning of those things such that for our weak solutions, this meaning, this makes sense. So actually, when I was preparing, I found some mistakes. So what we have here is, first of all, we, as in Rajesh, yes? Ravin talked yesterday. We have to take some test functions too. So what we want, we take a test function v from the space, probably slightly more regular. So take it just C2, doesn't matter, from D cross the closure in with values in R3. Yeah, so as a test function, we don't require functions to be with constraints, and we look what would be this expression v. But this expression is really the integral over dx. Yeah, so we multiply by v, integral, and then we would like to integrate by parts. The problem here is that how to do it. So if you write it down, you will see that the thing is here, and this is multiplied somehow by the expression of u and v. And using properties of vector product, you can write down that this is just equal minus integral. So we use the vector product, so we use only properties that the inner product of these guys becomes inner product of Laplacian u of x and u of x, v of x, dx. So what I change is I move Laplacian u to this part and u to put this one. So what we have here, you have a vectors a, b, c, and here you've got vectors b, a, c, and this is not this odd permutation. It's called odd permutation. So we put here -1. So this is some kind of property, and now we can really apply integration by parts formula, because this is just equal sum of a xi, sum of the I d squared over dxi of u. You have to be careful here because u is a vector, so sometimes writing formally is not really correct. But if we apply the integration by parts formula, what we'll get sum over I integral du over dxi, and here we'll have du over dxi of this vector product, which is bilinear. So we'll have du over dxi vector product v dx plus the same integral but u cross dv over dxi. And now about boundary conditions. Now, as I said, as Marco said, oh, who said it, I don't know, there's always problem which is the sign when you write down the boundary condition. But, so I wrote it plus minus, what we have integral over dd, and what we'll have is du over dxi, u cross v, and here we take nu I, d sigma x, respect to the surface measure. So nu I are the so nu is the normal vector field, as in the Stokes theorem, and nu i's are just coordinates of nu with respect to normal basis. So the other thing is that because we consider so nu I is a number, so and here is also the sum over I, so everything the sum is there. So if I go with the sum inside, I've got the condition which I have written over there, the du over dn. Oh, so okay, so then is n, so here should also be ni. 0, so the boundary term is 0. And there is one more simplification. Would you tell me which one is? One more thing which cancels? Would you be able to tell me? Which term cancels? So look at this vector pointwise. So here I've got one vector, scalar, and then I've got scalar product in R3 to a vector product of two vectors. So this vector product is perpendicular to both, in particular to this guy, but this guy is the same as this one. And so this vector product pointwise is just 0. So what we end up, we'll end up with just this formula, sum over I, du over dxi, u cross dv over dxi. And these are partial derivatives. So if u is a vector field function with taken values in R3, this is also in R3, so it all makes sense. So in this way, we have explained what will be the meaning in a weak sense of this term. So whenever we want to have it, we should replace it by z. And this is as in Navier-Stokes, it shows that we really don't need to have such strong assumption on u as to have a Laplacian u, at least from this point, this case. Now, the other term can be given similar considerations, and by similar arguments, you can show that the other term, which we can write the other term we can write down as the integral minus u of x cross product u of x cross product Laplacian u of x, and we take d of x dx, and after applying the same, so the main point here is that we use a different formula relating to the vector product and scalar product, so which means that what we'll use, you will get Laplacian u of x, so we put it here, and everything else on the other part. So I have here I have this version, but and then the procedure is more or less the same till that the term, boundary term, disappears, and what only remains is the sum over I du over dxi d over dxi v cross u. Cross u, possibly one can also simplify this term, but that's how we use. So this is what I explain is that if you want to define a solution, we need to define in a weak sense, PDE weak sense, but also contrary to the talk yesterday, where in case of dimension, space dimensions of D, when the set D was in R, in this case, I prove existence of strong solution in stochastic case, because I didn't change the Wiener process, but it was only for lambda 1, 0. Here, we consider a general situation, and we need to consider weak solutions, both in PD and probability sense. I need to make a break, sorry for this. So in order not to get you, how to switch it on? Provided I can really switch my computer back on. So I will send you, just to entertain, a picture, and later explain what this picture is about. Oh, does it work? Okay. So that's the picture. And Uto, you can put running again. I'll be back in a second.
Not bad, not bad. If you wish. No, it is not this part. Maybe this part you can. The last part, maybe for speakers, what is inherent is the additional comments and setting.
Here, and then you have a lot of points. So these a lot of points are really So these a lot of points represent. Play again, I don't know. represent finite element approximation of a curve which has values in the sphere. And then the numerical experiments are, there is a time running out. So you see at the beginning, the whole curve is somehow concentrated at the North Pole. And I believe, because I haven't really checked, but believe my collaborators that what he did is really about stochastic Landau-Lifshitz equation. And you see at this moment, what happened is that the whole somehow curve moved to the South Pole. So at the beginning, it started to be North Pole. And if it was deterministic problem, as I explained before, it would stay there forever. But because of the stochastic terms, these terms somehow push the curve from this neighborhood of the North Pole towards the South Pole. At some moment, they push everything. And what you see here now is back to the north. It stays for a long time at the south. It still can have some excursions. But in a sense, you can say that really now the curve is close to the North Pole. And this would repeat and repeat. Of course, the video has only 1.5 minutes length. So that is the video which I wanted to show you at the end, but I showed you now. Maybe I'll show it again. And that is the motivation, really, from this point of view of applications, where physicists really wanted to have a model where this transition between one station state to another and back is really exhibited. And that is what we proved. The paper is on the... yes. So it's not really transition between the poles, it's transition between neighborhood of the pole and neighborhood of the South Pole.
So you are able to describe how they go from one part to the other?
Yes. So, and to switch this off for the time being, is it red? So, I leave you those formulas for the time being, because when we write down the definition of solution, we will need this formula. And the definition of solution is really very much similar to the one which we had in other talks. So let me just write it down again. So what we can do, okay, that fit doesn't matter. So we assume that U0 is just element of H12D with values in S2. And and we also assume that the H is given in the space, I think, W13 or W14, sufficiently regular, but not. A weak martingale solution to our problem, to stochastic Landau-Lifshitz-Gilbert equation, which is this one, is a system, and the system is very long. So it consists of probability space, omega, F, P. It consists of filtration, and it consists of two processes, U and W. And W, so we started with W as Wiener process, but that actually what we say here is that we want to have another W on different probability space, but still standard Wiener process. So we have this one. So such that this is a filtered probability space. It satisfies the so-called usual probability conditions. W is F Wiener process. So, and u is a function from omega cross a plus with values in h12 of ds2 is progressively measurable and such that for what are the conditions? So we have a little bit more properties than this one. So first of all, we have property about continuity. So here we have the space here. We consider operator with normal boundary conditions. So we assume that we require that u almost surely is a continuous function from A plus with values to the dual to the space H12. And this process is bounded with values in H1, but locally bounded. B, I want to make precise this condition, that namely what we really want is that u of tx is equal 1 almost everywhere with respect to Lebesgue measure, so almost all Lebesgue measure x, and for every so for every t, this holds with probability 1. And now we have this weak version of our problem that for every test function phi, here I've got written W14, what happens? If I take u of t phi minus u0 phi, what we have? We've got, first of all, the term coming from this guy. And if I change the order between u and d over v, well, I change the sign. So I've got minus lambda 1 sum over I integral from 0 to t integral over d. And what we have there, we have du over dxi of s x. We change the order, so we have the test function first, dv over dxi of sx, u of sx, dx, ds. Then we need the term from the second term, and here we start with minus, and here we've got plus, and for some reason, my sign in the paper is different from this sign, but whenever you have signs, as you know, you always have to take into account that it's easy to make a mistake. So, modulo, we have minus integral from 0 to t, sum over I, integral over d, and here we've got du over dxi, du over dxi, but not u, but u cross test function phi. Phi is, so here should also be phi, because phi is a test function. Vector product u, dx, ds. And finally, we have the Stratonovich term, which I write for simplicity, integral from 0 to t, integral over d, u cross h, inner product phi dx Stratonovich dw. So that is our solution, definition of a solution. Now, can we prove existence of such a solution? So in order to prove existence of such solution, you need to make sure that the solution is such that actually all these terms which are here make sense. So implicitly, we assume that whatever is integration is makes sense, at least in the Ito sense, Lebesgue sense, etc. And therefore, and secondly, you cannot expect to get a solution without any a priori bounds. So the a priori bounds actually in our theorem will play double roles. The one role of the a priori bounds is that they will make that everything which is written here makes sense, and the integers are convergent. Secondly, it will give us idea how we can prove the existence of the solution, because in order to prove the existence, we will need to get a priori bounds. So as we've seen, so Razi talked yesterday, he started with certain lemmas that if you have solutions, then solutions satisfy some inequality. And that is exactly what we need here. So what we have is the theorem of the following form. So we assume that U0 is here. Actually, we assume that A is also bounded. So bounded and W13. And then there exists a martingale solution. Exists a, how did I write it here? Weak martingale solution. There exists a weak martingale solution to stochastic Landau-Lifshitz-Gilbert equations, such that this solution satisfies some additional properties. Property 1 is that expected value of integer from 0 to t, u cross Laplacian u of t squared L2 is finite. So, actually, we need to explain what do we mean by this u cross Laplacian u, because, and actually, the solution is actually written here, still there, because by u cross Laplacian u will actually mean a process which takes values in L2 space such that this integration by parts formula holds. So then the second property is that expected value of supremum over any finite interval 0t of UH1 norm to the power 4 is finite. Then, so let us put it property A. Property B is that actually this equation can be written in a strong sense. So this condition implies that we know what is u cross Laplacian u. So if you look at the strong sense, we can just consider it as an element of L2 space. So what we can say is that it is ut is equal to u0 plus lambda 1 from 0 to t u of s cross Laplacian u of s ds. Then, if we know that this guy is this process which I said, which has values in L2, and u is a process with values in a sphere, this guy will also have values in L2 because it's bounded. So we can also write down minus integral from 0 to t u of s cross Laplacian u of s ds. And finally, the Stratonovich term, which we have written, say, inter 0 to t u of s cross Stratonovich a dw of s. So this should be true almost surely for t largely equal to 0. And finally, that our process actually is Helde continuous, not only continuous as it was before, but with Helde continuous with values in space L2. So if alpha is less than 1/2, u belongs to C alpha 0t with values in L2. obviously for every t. And a common is that we can't really have bigger than alpha 1/2 because of the presence of this guy. And unless it's 0, this will never. Actually, unless it's 0, this term will always be at most held a continuous with exponent less than 1/2. No, so this is a theorem, okay? So the weak formulation is sort of direct consequence of strong formulation if we do the integration by parts formula tricks which we did before. And how can we prove this theorem? So I don't want to go too much in detail. Is it everything clear? But how would we prove it? Now, in a sense, a question, yes? So give me a suggestion. How would you prove the existence of such problem? Or give me some keyword. So what would be the keyword to prove existence? What would be the keyword? Sorry? Yes, we do some approximation. And Marco, or Professor Romito, spoke yesterday and before about Galerkin approximation. And the reason for doing Galerkin approximation is that the problem becomes finite dimensional. And in finite dimensions, we know how to deal with stochastic differential equations. There's no problem with weak solutions. Of course, you can have weak solutions and Strug, Varadan, etc. But when the coefficients are nice, there's no problem. And what are our coefficients? If you look at this equation, with respect to u, this is quadratic. This is polynomial over 3. This is linear. So the coefficients are all polynomials, like in Navier-Stokes. So when you do Galerkin approximation, because that's what usually we do, then the equation becomes of the same sort, so polynomial. And everything which is polynomial is C infinity, and therefore you don't need anything like Strug, Varadan, or any sophisticated things. So what we do is choose, choose the Galerkin approximation, or choose an approximation. Actually, one can do it two different ways. One can have Galerkin approximation, and one can also consider finite element schemes, which are probably better for numerical simulations. And what you have seen in the picture is sort of related to the other methods which I did with Andreas Proll and Lubomir Banach. So we considered an alternative proof of the theorem, but the original proof is on Galerkin approximation. So when we want to have Galerkin approximation, we need to choose a sequence of vectors En. So how would you choose this sequence of vectors En in this case? Is there any natural way of choosing them? How the sequence was chosen for Navier-Stokes? So for Navier-Stokes, there was an operator, the Stokes operator, which happened to be self-adjoint and of compact resolvent. Here we also have such operator, which is the Laplace operator with the Neumann boundary conditions. So what we consider, this is just, consider we define operator A with the domain H12 D with values in R3, intersection those U in H22, such that the derivative on the boundary is 0, and the operator A is equal minus Laplacian U for U in domain of A. and it is well known, so well known that I cannot really tell you where it was proven, that this operator A, provided boundary is smooth enough, is self-adjoint. It is not invertible because the constant functions make A 0, and the constant functions belong to the domain, contrary to the case of Dirichlet boundary conditions, agree? So, which is non-negative, but not invertible. However, if you take A plus identity operator, the inverse exists and is compact. And this implies it's compact because we always assume that the domain, the D, D is bounded. And so there exists a sequence Ej from J1 to infinity in domain of A such that A Ej is equal to lambda J Ej. And there exists also a sequence lambda J. And what we know is that the lambda J converges to infinity when J goes to infinity. There is some more precise formula that Shri was talking once in the lunch, that the J behave at infinity, something like, not J, but lambda J behaves like J to power 2 over D. Yes, and there's actually Y formula or something like that.
Should be better on a manifold.
Sorry?
That compact manifold, they should be better than.
No, it's always this way. Whatever set it is, it only depends. And then you have another part which depends on the characteristic of the manifold.
Spherical harmonics, but they are not right. They go like.
No, but you in this way what I consider is I consider them, these are eigenvalues in the way that, say, 0 is the first lambda, and then so I list them with the multiplicities. So if an eigenvalue has multiplicity 15, then I list those 15 times, and then what we have. And you are right that there are some situations where you know exactly what those eigenvalues are. And okay. And now when we have this, we just consider the space Hn to be the linear span of the first of those vectors. And what we do, we just write down the approximation. So one has to be careful with this approximation. And in the case which we consider, actually, I have not realized, only later, working with Liang, actually in November this year, we realized that the form of the equation should be of this form. So if I have an, I use the letter pi n, yes, because I'm Greekophobe. Right? So we use the pi n now for different purposes before. It's a projection from H, which is L2 space, into space Hn, orthogonal projection. And we are looking for a solution which takes values in Hn. So we're looking for solution Un taking values in Hn. So in order to have this one, what we have to look is Un over dt. And here we need lambda 1 pi n of Un cross. And here I have written before lambda n Un. And if I write down Pn, you say, why? You don't need to write down Pn because, not lambda n, it will be lambda. But if I write here Pn to lambda n, you say there is no need to write down Pn because the space Hn is invariant with respect to Laplacian. So the pi n is just identity. So, but I will explain in a moment why it's important to write down this way. And then we have minus pi n of un cross un cross. And here again write lambda Laplacian un plus, I think, un cross, I write in Ito form. So I think we all, again, have to write down pi and h. Although in the paper it's not written, but this will be better written by Liang. I hope it's always correct. And then we have the correction term. Here is dw, 1/2 un cross pi n h. And I forgot about pi n. So everything on the right-hand side takes values in hn, yes? The reason why I wrote here pi n was that if you have this additional term, the other energy, with the other energy would have term gradient phi of un. And if you don't add this pi n here, then the system is not so nice geometrically, etc. However, when we add this pi n, then it becomes much nicer. So this pi n is important when we consider the more general energy. In our case, when we have only Laplacian, this doesn't really matter. So in this case, we can really forget, but it is very convenient to have it in the more general case.
Is pi n also required?
Yeah, pi n is required. No, because un is in hn. But if you take un cross element, so in a sense, I don't know whether it is, means, I think maybe in some very particular cases you get back to hn, but I think not generally. So this equation actually can be written now in the form du of dxn. Here we've got some function, call it f1 of un, plus some f2 of un dt. Oh, I forgot to write that when we switch to stochastic, we should really write it down. du, we should write here dt, dt, yes? But that is, if anybody understands, easy to correct. It's not a mistake. So now the equation for un is f1 of un, which is this term, plus f2 of un, which is this term, plus g n of un dw, plus this term, which you can write down maybe f3 of un dt. Agree? And now this is equation in finite dimensional space Hn. And if we look at this equation, we said, as I said before, f1 is polynomial of order 2, f3 is polynomial of the 3, f2 is polynomial of the 3, f3 is polynomial of order 2 respect to un, and gn is linear respect to un. So these are local Lifshitz terms. Local Lifshitz means exists local maximum solution. Local maximum solution, you have some stopping time, and you can prove that if you approach the stopping time, the norm would have to explode. And the way to prove that this local maximum solution is really global solution, it is so-called Hashminsky test, is that you can really control behavior of the norm of the solution. If this norm does not explode, then the solution will be global. So, is there any reason this norm would not explode? So the reason is the same as the reason is that we can get these a priori estimates. Actually, I have not written it in a way which I would like to write, but first of all, let us look at, so UN, okay, so let us look at UN squared in the space Hn. Yes? And then we apply the Ito formula to this expression. So we apply Ito formula and put here 1/2. And what we get, we've got UN of T d UN plus 1/2 of the second derivative of this function. This function norm squared, second order derivative is identity. So it will be 1/2 identity acting on these two guys. So what is these two guys is, so it will be norm pi n of UN, put here pi n of h, doesn't matter, squared dt. That's our Ito formula. What we notice here is that this guy with respect to UN is linear, so we'll have some linear growth to apply Gronwall lemma. Here, we'll have term with W, which will be actually a martingale. So when we take the expected value, the term with will disappear. Expected value will disappear. So what remains? What remains is the product. So the du is this guy. This we take because after taking expected value will disappear. The F3, so we take 3 terms. So what we have will be UN F1 of UN plus UN F2 of UN and plus UN F3 of UN and other terms. Now, what is this guy here? This is the inner product in Hn, which is the same as inner product in L2. So I've got UN pi n of something, yes? Pi n of what? Of lambda 1, which I can get here, of UN cross Laplacian UN. Pi n is orthogonal projection in this term. So what it becomes pi n of UN and UN cross Laplacian UN, correct? And pi n of UN is UN because it's, so what do I have? I have some just UN. And this is inner product in L2. So it is pointwise, but then pointwise this is 0. So this is 0 pointwise because we've got this UN vector product something and pi n there. Now if you look at the structure of F2, it is the same structure. UN, you go pi n over there, pi n disappears, and then you've got something which is orthogonal to UN, which gives 0. And F3, what was F3? And F3, actually I don't remember how it will be F3, but so here will be 0. In F3 we'll have UN. F3, it's okay because use the correction term. So with UN pi n of UN cross Hn, and the same trick goes. So all these guys disappear, and if there was actually no stochastic term, we would just get 0 and with the constant. In stochastic term, we have this guy here, but this we can apply the Gronwall lemma to prove the global existence. So first of all, we have a global existence of this problem in Hn, but we need more because we need this sort of inequality property. And then we apply another norm on this space Hn, which is equivalent to the norm in H. Equivalent because every norm is equivalent. So what we apply Ito formula to the form gradient un in L2. So instead of doing these calculations, I just want to show you how this calculation would be on this level. Because these things are very similar, and they work, and we get this a priori estimate because they work on the formal level for the equation, full equation. So let me.
So if there is no stochastic term, then this is equal to 0, right?
Sorry?
There is no stochastic term, it has to be 0.
Yes.
Except that.
No, this term is stochastic. This comes from the.
So that means U is a constant.
If the deterministic case, it will be constant because you have to remember the deterministic case, the norm of U is constant. For every x is 1. So L2 norm is also constant. So it's even more. The point is that on the level of.
Your initial data is some U naught, that is not a constant function.
So L2 norm is constant.
But L2 norm is constant.
Oh, L2 norm. Because it is an S3.
L2 norm is constant. So there is something like, for say, if you take strong solution to Euler equation, then the L2 norm will also be constant. Yes? So that is this sort of problem. So instead of looking this one, let us look at this expression. And again, we use, when I say Ito formula, I wrote here D on the right, but I should have written D on the left as well. So what is, so let us write D of that one. Oh, maybe I will, so what we need, so this is our function phi. Phi of U is, and what is the derivative? So phi prime of U on the direction V is just gradient U, gradient V, or we can also write down as minus Laplacian U and V. And what is phi dot? It's the second order derivative. Because it's quadratic, this will be constant. And in any two directions, V1, V2, is just gradient V1, gradient V2. Correct? And let us see what we'll get here. So by Ito formula, we've got phi prime of U d du. Okay, so it will be like that maybe. And then we have the correction term, 1/2 phi b's of U acting on those directions. So the Ito direction is U cross H. So we've got U cross H, U cross H. Okay? So what we have, so phi prime of U is minus, put it Laplacian U, and then I write it this way, and then you have V, so here should be D, so instead of V, we write du, but du is lambda 1 U cross Laplacian U minus U cross Laplacian U, and plus U cross H dw. That will be correct. And the Ito correction, no, it's not of the Ito correction because I forgot about this term, U cross H cross H. So there is also, so here is everything dt. And there's also term U cross H cross H dt from the Ito correction. And what we have plus 1/2, which will be identity. So we have U cross H squared dt. Agree? This is on formal level. And actually, this is only on formal level. What the same calculations can be done rigorously on the level of Hn. But without understanding those, we wouldn't be able to do the others. And what we have is, so let us look. What about, so we expand this inner product, because this inner product is in L2. And then we've got the first of all inner product is this guy with this guy. What is it? Zero, because we integrate pointwise, and for every x, this is orthogonal vector in R3 to this vector. So this guy gives us 0. Mentioned analogy to Navier-Stokes equation. When you do energy estimate for Navier-Stokes, the term coming from the Euler case disappears as well. So it is a sort of similarity. Then we have this term where I have minus Laplacian u, here's u minus Laplacian. And there's a formula which I already used, that if I have inner product of one vector and then you like those, this becomes minus u cross Laplacian u squared, and this gives t. The sign is important, and it has to be minus here. This guy, actually, we don't need it here, but so this guy, after we also take will apply expected value, so it will disappear, so we don't take. But we have this term and this term, and for this term, the best way is to put the gradient back on this side, and so what we'll have plus gradient u cross h, and something, and would be dt plus u cross h L2 squared dt. And what you see here is that now it is this minus sign here. This is a bad term because we couldn't get rid of the Laplacian. We had two Laplacians, and the only way it happened is a miracle that we get this expression with the sign minus. The same miracle about which I spoke yesterday. So when we took this into account, what we at the end obtain is at the end we obtain the formula that 1/2 gradient u of t squared L2. Expected value, because I want to get rid already of the term martingale term, plus expected value integral from 0 to t u of s cross Laplacian u of s squared ds is less than equal 1/2 expected value gradient u0 squared L2, and plus these terms, which can actually be estimated in terms, so this is bounded because u as this is bounded. So this, but this term can be estimated by constant times gradient u. So what we'll get is plus some constant n plus some constant b, integral from 0 to t, gradient u of s squared L2 ds, expected value. And this inequality can apply Gromov lemma, in particular, implies this condition. It implies this condition with 4 replaced by 2. But if we know how to prove it with 4 replaced by 2, we also know how to prove it for 4, which is important, etc. So what we have is that we get those a priori estimates which are obtained in principle by this way, that if you start with the full equation on formal level satisfies these a priori estimates. And now, what is next? It is a lot of work to do because you have to make sure that your a priori estimates actually are working, because most of these a priori estimates gives you convergence in a weak sense. And because of the nonlinearities, you have to identify various objects. So you have to prove there is one solution. So something which was mentioned before, is standard in nonlinear problems. And in particular, you need to have some strong convergence. One important tool is Skorohod embedding theorem. I don't know whether it was mentioned that if you have a sequence of processes which have some uniform bounds, then you can prove that in some sense they are weakly, they are tied in certain, the laws of those processes are tied in some topology. So they exist as subsequent convergent in a weak sense. And the Skorohod theorem says that actually there is another property space that the convergence is strong in, and applying the Skorohod theorem, at the end you need some strong convergence in the, not weak convergence, almost weak convergence probability on the new probability. So what we have is that we have some law of UN converges weakly to some law of some, doesn't matter, but then in the Skorohod theorem implies there exists a new probability space such that the processes UN, call it tilde, converge to U from almost everywhere, but in the topology which are there, but almost everywhere P tilde. Then this new process still has to be somehow strong, convergent, and not weak in some Hilbert space, etc. What we get in our case, we prove that our processes satisfies this condition that UN, integral from 0 to t, UN of tx minus u of tx to power 4 dx dt, this converges to 0. So in fact, converge strongly in L4, L4. And this is the crucial point in order to identify various objects we obtain by this weak approximation. And so all these things actually are not yet in the notes. So the notes will be even longer. I will put them in the notes because I found some mistakes in my early notes. But the idea is this one now. So sort of how to prove the existence of weak solution is you use Galerkin approximation. If you are lucky to find a priori estimate, then you have them, and then you know to proceed. If you don't know a priori estimate, you are dead. So the a priori estimate is your first bridge. Without a priori estimate for nonlinear problems, you are done, and you are dead. Yes. And once you have your a priori estimate, you are more or less know how to proceed. But there always are many ways to get. It means you know where you aim, and sometimes you get, sometimes you don't get them. So I wanted to finish, but you have already seen the picture. Maybe show again to have it nice. So this is a picture done, again, repeat, simulation when X is one dimension. So the material, the magnetic material is very thin, and we have certain noise. And with this noise, we have sort of proved that this conjecture of physicists is really valid. Yeah, so, okay, it shows on my picture. It will take some time. Is it okay, or I did something wrong? Because it shows here, oh. So as I said, we have some configuration which start originally near the North Pole. So you have like a magnet, the magnetizations are all situated to that pole. And then they fluctuate because they fluctuate with noise, but at some moment they become attracted to the bottom and stay there for a while, and then they move up. And I think understanding better, there's a paper by myself, Goldis and Jagaraj on the archive, without the picture, but which is exactly theoretical underpinning for this picture. Yeah? And I think going further in this direction will be very interesting, especially if there are some applications, as we have heard from one of your colleagues, who is working on deterministic Landau-Lifshitz equations. Yes? And Liang is working on this generalization I told you about earlier. So thank you very much. And questions?
So in the generalization, what is the hypothesis you put on P?
So actually, here we've put phi, because phi is actually defined only on the sphere. So what do we assume on phi? C1 class or something like? Not mine, because in fact, because phi is defined on S1, you are not. If it's continuous, immediately bounded. So you don't have the sort of things that you would say would be growing infinity, because the state space is compact. So we just, the only assumption we make is a regularity, which is probably C1, maybe C2, I don't remember. Of that sort, yes. And but then the more difficult situation is, which started very recently, but there was a plan earlier to consider magnetic fields, interaction with magnetic fields, and but then I don't know exactly. He started discussing with Goldis in November, so that is also a work in progress. Yeah, so there is also like a term of in energy, and this various term in energy are in the notes. I have written more or less copied what was in Visintin's paper, which I meant. Sorry? As a magnetic energy, I think is linear. I think if you have an external magnetic field, I think the energy somehow is integral over d u h, something like that. So it's linear. That's how it's written. So I mean, I didn't mean go into physical things to check whether it's correct, but I think it's linear. Yeah. Sort of.
Change the target manifold.
Sorry?
Change the target manifold S2 to something like that.
I mean, there is one paper which I know by some Japanese, but I can send you details when I find, because we considered the S2 in some special manifold. But because if you want to change it to different manifolds, you can easily change, as I said yesterday, the heat flow. But when you want to have the full Landau-Lifshitz equation, you need to understand what is the meaning of u cross Laplacian u. What do you want to replace it by? And I think you need some special structure of the manifolds where you can have maybe Kähler manifold or something like that. If you don't have this, then I don't know how. But there's this one paper, and I think it only studies local existence. Repeat, these equations have sort of like Navier-Stokes, in the sense, because they have motivations in some physics or some applied science, you don't really want to modify them too much. The freedom is restricted, yes? Of course, it's interesting, etc. I like this point, but there are many problems already for those equations. I said that in any dimension we have existing weak solution. Yeah. In dimension 1 we have existing strong solution. In deterministic theory, it is known that in dimension 2 there is a finite number of singular points of every solution has. Outside it's smooth, and now what is true in stochastic case, and whether the stochasticity could influence those points, which is kind of a dream, but one should try to see what the question of invariant measure is another problem, which you don't know, and it's what is the large time behavior. So there are many things, but also it is quite technical problem in a sense. So if you go into, you need to spend a little bit of time to learn.
I have a question. This is about the
Okay.
phenomenological
Okay.
First, there are evidence in the physics community to consider Gaussian noise.
That is what they say. I can give you references. And actually, what they all, and I mean, I've read, I don't remember where exactly because I read those things, but it is the motivation is they say that you consider in experiments of switching between different station solutions. And if you have purely deterministic theory, it does not allow it. Because if you are in...
Cannot go from one domain to another.
Yeah, because it's... Yeah. So the noise is here something which they really predicted to use. Yeah.
In terms of temperatures, it must affect more the so-called fast variables, the variables that, for example, gives predictions for 1 week, or the slope variables.
I don't know this yet. I mean, I mentioned the word name Chantrel, and I have you really want to understand better from him what it is, and he actually used the word fast variables, etc. So I don't know what they mean from that point of view. I'm going to meet with him often to learn from physical point of view what does it mean.
It should be interesting. For example, this model gives somehow fast variables. Couple the model with some equation, we'll see for reaction between one that gives you fast.
Yeah, concerning coupling of equations, I should mention that there is another model which actually couples these things. So, and again, something which is used in physics, but in this case only in deterministic case. Right? So in Landau-Lifshitz, this kind of a physical works on the suggesting use the noise. Here you only have here you only have the coupling in so which is called indeterministic setting, not studied in stochastic, and it is called liquid crystal equation. So you have u, which is your velocity, and your particles are kind of elongated particles. And so there is a director, which is called d, which shows you how this particle is positioned. And then the equations for, you have two equations. So you have equations for u. I don't remember signs. Then it's something like divergence or gradient of gradient d, some sort of this way, and then you have the heat. So this is the, and then you have the heat flow for d. So it's dd over dt equals this non-linear Laplacian. So in this case, we can actually write down minus d cross Laplacian d, because we take d to be of norm 1. But there is a term, like a diffuse transport term of d in the direction u. And it happens that actually you get some a priori estimates, because these terms happen to be such that if you multiply this by u and this by d, these are strange, but they cancel. Maybe, yes, I don't know exactly the reason, but they cancel. And means, so again, you got a model which was proposed by physicists, but nobody studied in stochastic case. But you can say, okay, once I studied Navier-Stokes, I can study this as well. One way to look at it. But it is coupling, the same as you say, but it's coupling. You can couple maybe with something else. And I think this is a good idea what you said. I just only wanted to say is that there is a coupling possible like this one.
I am curious about models that use some dynamics, structure dynamics in the slope variables.
So for me, using slow and fast variables